Okay, we got the recording. I'll repeat just briefly what I said. Let's see, be sure and everybody check your email. And I sent you a bunch of files today. I've not sent you that EPRI report, but I did send you a homework assignment. So I may put that off until the first of next week because you already have something to work on. So I don't want to pound you too much. Oh, I sent you your project description, which I think I gave you 6 different topics. And the assignment is to do a PowerPoint presentation uh, on those topics. It was like solar, photovoltaic, solar thermal, wind power, geothermal, renewable technologies to generate electricity. I guess I can't cover everything and all the renewables too, but giving you that project assignment will get you out into the world of renewables a little bit. I'll continue to send some links to YouTube videos. I think we'll do one on probably wind. There's some good stuff out there on wind, maybe geothermal. I've got a couple short ones queued up here that'll give you a little bit of information. So that's kind of where we're going. So I want to wrap up the thermo stuff today. So I've got several little files queued up here that we're going to go to. And we're going to work some example problems, a couple, go through them on the Brayton cycle. But this concept gets used that I'm going to talk about today. And so I don't know if you're going to remember this from your thermal or not. But so I thought this is scanned out of the thermal book. So if you still have your thermal book, you probably still have this exact section. But so this is looking at for an isentropic process with a gas. Well, so in a Brayton cycle, we got a gas. It's typically, we assume it's air, and we definitely are doing some isentropic processes. So this is going to apply directly to stuff that you see in the homework solution. And so over here, you just have a TS diagram with, state 1 at lower temperature and state 2 at higher temperature. And these little swishy lines are just lines of constant specific volume, pressure, and temperature. They don't need to be there for our discussion, but anyway, the author of the book wanted to put them there, so they're there. Okay, so this equation in general is for an entropy change for an ideal gas, okay? And so because this section is talking about isentropic processes, the entropy change is 0, right? Because that's what we mean by an isentropic process. And so you see on the TS diagram, we're going to go from 1 to 2 straight up because entropy is not going to change. So this is an equation we can use to apply to the process going from 1 to 2 isentropically. And so you see we've got, 4 variables in here. We got T1, T2, P1, and P2. And so, and it's set equal to 0. So I can know any 3 of these and solve for the 4th one, right? 1 equation, 1 unknown. So that's pretty simple. And this stuff, these S superscript zeros are functions of temperature, and they're in the ideal gas table. Okay, well, and let me go ahead and pull that table up. We'll bounce back and forth here. I've got it right here. In the thermal book, it's table A22. And that's right, I emailed all these tables out to you the other day. It's handy to have, digital copies of steam tables around. You might carry those with you, after you graduate and you're out there slogging around for a living and you go, man, I wish I had my thermal tables. Well, by golly, if you got your computer, you do. So they're handy to have. So, so here's the S superscript 0. So they're tabulated as functions of temperature. So they're just straight lookups. Okay. Yeah, back here. All right, and so that's where those come from. R is just the specific gas constant for whatever gas, universal divided by molecular weight. And, these are absolute pressures. Okay, so if we go down here. So then that's what he's talking about. He say, well, let's say we know T1 and P1 and P2, then we can obviously solve for S superscript 0 of T2. And so you plug in all the numbers on the right and you turn the crank, and so you get a number, and then you go back and look in that table on the S superscript 0, and you can interpolate, and you can find the enthalpy and the temperature and all the other properties, right? Because you've calculated this S superscript 0. So that's one example of using that. Well, another way we can juggle that equation, let's say that we know P1, T1, and T2. So just doing a little bit of algebra on that thing, then you can say P2 is going to be P1 times exponential of, all that stuff in the bracket term, okay? Pretty straightforward. Now, for air, and only for air, we have this special tabulation, and it's called relative pressure. And so here's what they have done. Now, don't ask me why this isn't done for other gases. I guess because air gets used in thermo books a whole lot more. I don't really know why. I mean, it could be done for any gas, but as far as I know, the only tables that you can find that have this in it are for air, okay? But now, that may not be right, but I've never seen any. Well, so if you take this equation up above that you can't see and just rearrange it, it's pretty clear that I can write this 640C in this form. My algebra is not real good, but I think I can figure that out. And so what happens is this exponential S superscript 0 of T2 over R is tabulated, okay? And it's given this name PR2. So this is the definition of PR2, and the one on the bottom is the definition of PR1, and they're solely functions of temperature, okay? Because there's nothing in there, because the S superscripts are only functions of temperature, and R is a constant, so they're all functions of just temperature. And so for air, and this is for isentropic only. I mean, this applies directly to an isentropic process. The ratio of the pressure ratio is the same as the ratio of the relative pressures, and the relative pressures are tabulated in table A22. You got there, and you got a column here, and these go with, like at 200 K P sub R, the relative pressure is 0.0333. And so this is very handy when you're working these problems to use this relationship. And so I'm going to show you a couple of solutions here in a second, and that's what gets used. So I wanted to make sure that everybody was together on what I was doing. Okay. And so, and just note that the reduced pressure is different. Reduced pressure, reduced pressure, reduced temperature. The reduced pressure is the pressure divided by the critical pressure. So that's different than relative. And of course, they're both P sub R. And I have to go look up the name every time because I forget which one is reduced and which one is relative, But anyway, so long as you remember how to use them. And then, so they also do this little thing with, it's called a pseudo-reduced specific volume. And so what they do is they come in here and they say, okay, let's form the ratio of specific volume 2 over specific volume 1. And let's just use the ideal gas law. So we know PV is equal to RT. So you solve for V, which is RT over P. And so this is going to be RT2 over P2 divided by, or times, P1 RT1. So that's just writing the ideal gas, and then this one's divided so it flips up, so they didn't want to write it as a fraction. And then you can substitute in from this relative pressure. You got here, you got the the ratio of what, P1 over P2. Well, P1 over P2 is PR1 over PR2. So they substitute that in here. And then these guys get tabulated as this pseudo, they call it the pseudo-reduced specific volume, I think, or pseudo, yeah, I think that's what they call it. And so you can use that in the solution of problems. And so what you usually have to do is, if you're going to use that, you can get a number for one of these things, and then you have to go back to the definitions, and you can actually back out, you know, a temperature or something. You can go back to this definition and do calculations on it. Now, we're not going to do that with the specific volumes. That doesn't really come up in these Brayton cycle problems. But you know, while I'm talking about it, I figured I'd talk about both of them. Here's your V sub r's and here's your P sub r's. It says up here when delta S is equal to 0 to try to remind you that you can only use those for isentropic processes. Okay, it's the same way over here. Okay, so hopefully that's pretty clear. Yes, sir. Yes, yes, yes. And I guess I should have scanned the next page that has that on there. Yeah, it does. Yeah, I should have scanned that next page. When I scanned it, I was looking for the pressure stuff, and then I saw the specific volume stuff on the bottom, so I figured, and then I never went back and added that last page. But it is in your thermal book, or you can Google it and find it. Okay. So now I sent you this. This is just some example problems. I don't know where I got them. Just some diagrams up here above, but we've already kind of talked through this stuff, so I don't think we need those. But I thought I would just show you quickly how this stuff is used in pretty simple problems, which is a good thing. So, you know, we've got a Brayton cycle, just an air standard, ideal air standard Brayton cycle. Inlet condition of 10 or 100 kPa and 300 degrees Kelvin. Let's see if I can get that there, get it all on there. They give you a volumetric flow rate in a lot of these problems, which means you got to eventually calculate a density or something to get to a mass flow rate. And they give you the compressor pressure ratio of 10. So that says if I'm 100 kPa going in, I'm 1,000 kPa coming out. Okay, but you really, I mean, if you have the pressure ratio, that's really all you need in working the problem. Let's see, turbine inlet temperature is 1400 K, and determine the thermal efficiency of the cycle, the backwork ratio, and the net power in kW. So let's go ahead and look at this. So there's the diagram. That's just what we've been looking at. You know, compressors 1 to 2, heat exchanger where the heat is added, 2 to 3, get the high temperature, 1500, go through the turbine, nice and isentropic, everything's straight up and down. And then basically we got to close the cycle, we got to show this kind of imaginary heat exchanger, like we're rejecting heat to get back down to here, because 4 is considerably hotter than 1. So that just closes the cycle for us. Okay. So let's just look and see how this goes pretty quick. Okay, so you typically start over there going into the compressor. So you've got a temperature, you got 300 K, so you just go to table A22 and look up the enthalpy. So it's 300.19, and you're going to go ahead and look up PR1. So we'll check it. We're not going to check all of them, but we'll check this one. So There's the enthalpy, 300.19, and there's P sub R, 1.3860. And those are the numbers that we had. Right here, okay? And so since it's isentropic, we can apply this directly. And so we say we're going to calculate PR2. So we know PR2 over PR1 is equal to P2 over P1. You get to hone your interpolation skills here quite a bit. So 13.86. Let's see. I have to go down there. A little bit. Someplace in here, there's 13.5, and there's 14. So we're kind of in between here. So we've got to do the interpolation. So we're between, what, 570 and 580 Kelvin, and our enthalpy, oh, I don't know, it's probably someplace around 580, someplace in between 575 and 586. Just interpolating that. So we go back over here. And okay, so we're almost 580. So he says we're 579.9 when he does the interpolation. Okay, so for an isentropic process, that's the exit enthalpy at the compressor. So bingo, you got it. And then we do the heat addition, and that boosts us to 1400 K. Well, so I need an enthalpy, so I'm just back to the table at 1400 K. And I look up 15.4, and I also notice PR3 is 450, okay? Well, now I'm ready to go across the turbine, and it's isentropic, and so, you know, PR4 is PR3 times the pressure ratio. Well, the pressure ratio now is dropping, so instead of multiplying by 10, I divide by 10, and so this gets me PR4 at 45.05, and then I'm back into 45.05 tables. Where's 45? On the next page. Oh, 05, so I'm between 780 and 790 and 45.05. So I'm probably pretty close to 810, 809, 810 on enthalpy. Just interpret. 808.5. A didn't bother to give temperature. I mean, you could if you wanted it. And then, so you got your enthalpies. Once you got your enthalpies, then you just plug in the definitions. So the turbine is H3 minus H4. We got to subtract off what the compressor's doing, which is H2 minus H1. Plug in the numbers, and then the heat addition is H3 minus H2. So just plug in all of our enthalpies, and we're getting about 45.7%. The back work ratio is the compressor work input per unit mass, H2 minus H1, divided by the turbine work output per unit mass, H3 minus H4. With the numbers, we're about 39.6%. Okay? So, man, those relative pressures, man, don't shy away from those things. They make your life so easy. But it's got to be air, and it's got to be isentropic to use it directly. Now, let's look at one. Oh, let's look at this one other thing here too. So, you know, this is just ideal gas law stuff. Okay, so specific volume is, this is universal gas over molecular weight times the temperature divided by pressure, okay? And so mass flow rate is what? Volume flow rate divided by specific volume. So this is cross-sectional area times velocity, and that's this 5 meters cubed per second. So the AV term is 5 meters cubed per second, and then you got to divide it by the specific volume, which is right over here, and that converts from this volume flow to a mass flow. So, you know, that oftentimes shows up in these problems too. So, and then so to get the total cycle work, you got to get the mass flow times the net work. So this is what the turbine's doing minus what the compressor absorbs. So the difference times the mass flow with a little unit conversion comes out, what, 2481 kW. Okay. All right, let's go on. The pressure ratio is 8 instead of 10. I think the conditions is so anyway, you can follow through here. This just shows where all of his numbers, but this is isentropic, the one I want to get to. So in the next example, he takes this one as the base and then puts an isentropic on everything. And so, you know, these are his isentropic numbers. This is the isentropic exit enthalpy at 2, coming out of the turbine at 4, compressor work 244.16, and then here's what your isentropic turbine is doing, 606.6. Okay, and so he's getting a cycle efficiency there of what, 40? No, well, that's the backwork ratio. I'm sorry. Backwork ratio of 40.3, cycle efficiency of 42.6. Okay. So here's what he's doing is, so now the compressor has an isentropic efficiency of 80%. So it's 0.8. So this is your isentropic work. And so you got to divide by 0.8 because this real compressor requires more energy, more input. So the real compressor is 305.2, okay? And then the turbine, it's 85%, and so the turbine's producing work, so the real, or the isentropic turbine produced 606.6, but we're only gonna get 85% of it because we're only 85% isentropic efficiency. So the real cycle, the compressor work goes up to this, and the turbine output goes down to this. And so the backwork ratio jumps to almost 60%. And now, so he's got to get the enthalpy coming out of the compressor, the actual one, okay? So what he's going to do is he's just going to use this definition, compressor work, which he knows, 305.2, is the exit enthalpy minus the entering enthalpy. So he knows the entering enthalpy and he knows the work, and so he's just going to use that to solve for H2A. So that's what he's doing in this expression. And so this is the H1 is 300.19, and this is the compressor work, so you got to add those together. And so now this exit enthalpy on the actual is 605.39, and he even went back and interpolated in the table to show you what temperature that was. You know, you can just take, you could take this enthalpy back, you know, and just do an interpolation with temperature, and you find out it's 598. I don't know if that was really asked, but he did it anyway. And let's see, so this is Qn. So this is H3. This is just a lookup at 1300. You're told the temperature going into the turbine is 1300. So that was just a lookup. And then this was calculated by, this is H2A right here, the 605.39. So the required heat input is 790.58. Let's see, and I think I skipped over, did I skip over this one? think he had to do the turbine. I may have skipped past something here. Let me see. Is that right? Oh, that's all right. I thought he did the turbine too. Let me see. No. Okay. Guess I made that up. Okay. Well, so you know, we had the net work, which was just the turbine. This is the turbine work minus the compressor input, so that's 210, and then the heat input is this 790. So that's H3 minus H2A. So anyway, just shows you that you can use those relative pressures. Oh, okay, here. I know he did the turbine. I just couldn't remember where it was. Okay. So this is calculating the actual enthalpy out of the turbine. So it's the enthalpy in, well, the turbine work, net work, which we already know, is H3 minus H4A. And so you just turn it around again and solve for H4A. And so that's the enthalpy at 1300. And that's the actual turbine work, which was 85% of the 606. And so that gives us the enthalpy out of the turbine. And then he goes back and looks up the temperature just to show how the temperature changes when you have the isentropic efficiency present. Okay, well, that's enough. There's another example on here, which is a small combined cycle. Wouldn't be bad to work through that, but I think you guys have seen plenty of this with other thermos, so I think you should be pretty good. Okay. So let me see. I think that is going to finish the thermo presentations. Let's see. Yep. Okay. So right now we're going into what I consider the second block of the course, and we're going to spend some time in the Babcock and Wilcox book. So we're going to look in some detail at utility boilers, and then we're going to look at turbines. You get some idea, just some of the details on how this stuff gets constructed and what it really looks like if you go out there in the field. Okay, so I apologize. I've not emailed this out. I don't know that I can stand to email these out, but these are Lord knows how many years ago I wrote these. You know, this is kind of introductory stuff, and I just want to talk through some of this. I got a couple of YouTube videos we're going to go to introduce a couple of these other energy sources here. So this kind of comes out of the first chapter of the steam book, but you know, we typically in the Rankine cycle we use water as the working fluid. And you know, I mean, I guess, I don't know if you ever really thought about it, but water is known affectionately as God's gift to heat transfer, because it's just such a wonderful working fluid for us. So, and these are at least 4 reasons. You can probably come up with some more. But the first is high heat capacity. And if you look at the specific heat of water, at least in US units, it's 1 BTU, what was specific heat? BTUs per pound mass per degree of temperature change. And I mean, it varies with temperature a little bit, but in, you know, around 70, 80, 90, 100 degrees, it's basically 1. Well, if you look at air, that same temperature range, it's 0.24. Now, I mean, you wouldn't really want to transfer a lot of heat with air, but, you know, so I mean, water is 4 times better than air. If you look at motor oil, what's the specific heat of motor oil? Something I don't know, 0.6, something like that. Look at all the different fluids out there and compare the specific heats. And what you're going to see is water is a really high number, which means that for a given amount of water, you change the temperature, it can carry a lot with it for you. It's pretty darn cheap. In a lot of cases it's free or almost free. It's abundant, it's non-toxic. Those are all really good characteristics for a working fluid. So we like water as a heat transfer. Flow rates, as far as steam, it can be, you can buy little bitty process boilers, small, 500 to 1,000 pounds an hour, or you can go up to like TVA at their biggest power plants. What is it, outside of Clarksville? Can't think of the name of it right now. A 1,300 megawatt unit is someplace around 10 million pounds an hour. That's a boatload of steam. That's a boatload of steam. Steam conditions, well, if you're just doing heating, maybe your atmospheric pressure or slightly pressurized, 212, 250, something like that. That big boiler, that 1300 megawatt unit is supercritical. Critical pressure is 3203.6. Critical temperature is 705. So that supercritical unit's running in the neighborhood of 4,500 PSI and 1,100 Fahrenheit. That's pretty darn aggressive for steam conditions. Fuels. Well, back in the day, it was coal, natural gas, and oil. Now we got coal on the decline, natural gas on the increase, because it's cheap right now. Oil is flat to going away for power gen. It's just too expensive. Nuclear, someplace around 20% is the number I remember. So it's a significant player. Be interesting to see whether we see more nuclear plants or not. There's modular nuclear reactors that are being developed at Oak Ridge and some other places. And, it's possible that, large companies, Eastman Chemical up in Kingsport, could put in a modular nuke and generate their own electricity with it. Now, whether they want to do that and want to fight through all the permitting and all of the time that it takes to make that happen, we'll see. It's hard to predict. The industry rocks along, like nuclear was going gangbusters, in the early 60s, something like that. And then we had, 3 Mile Island and Chernobyl, and bam, I threw the brakes on everything. And Watts Bar sat there forever, and Belfont still didn't get completed. And there's reactors all around that were in different stages of completion. And sat there for a long, long time. And I guess, was it 2000? Something like that. TVA decided, late 1990s or 2000, TVA decided to complete Watts Bar 1. I don't know exactly the date. And then they decided to complete Watts Bar 2. And they're both operating, producing a lot of electricity with zero emissions. But you do have nuclear waste, which is a small amount of bad stuff that you have to take care of. So we'll see. It's funny. The industry seems to get in a particular state and it'll rock along for a long time and nothing really upsets the apple cart, and then something big happens. To nuclear, the accidents happened. To coal, CO2 emissions became very unpopular, and fracking came along and made natural gas almost as cheap. And when you consider all the other cost of coal, it made natural gas cheaper than coal. And so people are abandoning coal for, the power plants sit there and pound their chest and say, look at what a great guy I'm doing reducing CO2 emissions, but really they're smiling all the way to the bank because they're making more money with natural gas. Yep.
Does anybody look at, even though it's tiny stuff, right? We look at how fusion is coming along.
Look at what?
Fusion, nuclear fusion.
Ah, well, yeah, there's a lot of research. They can do, well, I don't know, they can do a fusion reaction for what, 1/10 of a second or something? I mean, I don't know. You track fusion?
I don't know much about it myself. I know the NRC, I've seen some upcoming meetings by then, they're talking about looking at what that kind of license.
I mean, that's centered in Europe. Yeah, France. Yeah.
Model reactor, but they got the concrete base done, I think. It's going to be a while before it's even up or people that stuff.
Well, you know, it's like they used to, when I was your age, they used to talk about fuel cells for automobiles and power gen and all that. And the fuel cells have come a long way, and there are some that are starting to make it to the marketplace. But as far as widespread applications, the word back then was, man, in 20 years, we're going to have fuel cells all over the place. And you ask people today, say, well, 15 or 20 years, we're going to have fuel cells all over the place. So, I mean, fuel cell, it's a very viable technology, but they require some pretty exotic materials that are pretty expensive. And, you know, I know John Zhu here works on materials research for solid oxide fuel cells. I was on a grant with him years and years ago, and he had some metal. I forget what the alloy was, but it was cheaper than some of their standard metals at the time. And so he was wanting this thing, he was wanting to make a fuel cell out of it. And we had to have some machine shop cut all these little grooves, little channels in there so it would work. It was my job to find a machine shop to get all the little grooves cut. And we looked and looked and looked, and finally up in Oak Ridge, we got some company to do that. And I don't know, we paid them, I don't know, $5,000, $10,000, you know, whatever it was to make 10 of these things. And man, they came back to us and they said, man, we were cursing you. That daggum material, whatever it is, it's hard as a rock. I bet we broke, you know, on their milling machine, the bit or whatever they call it. He said, oh, I bet we broke 10 of those things on this thing, you know. And so, and then they went on to try to stamp those things, you know, because I mean, it's a whole lot cheaper to take a big press and go kaboom, and they're there. I don't think that ever worked on that material. And so research goes on. So, you know, one of these days, maybe, I mean, it's certainly possible. We know a lot about it, but I mean, I don't think there's any fuel cell powered cars out there. There may be, you know, some demo units, but I don't know of anybody that's producing them and selling them, you know, in bulk. So anyway. Okay, so the common fuels, and then, you know, others, biomass and products, peat, you know, which is a type of biomass, wood waste, bagasse, that's what, leftover sugar cane after they pull the sugar out of it, straw, coffee grounds, corn husk, mine waste, solar energy. I mean, all of this stuff and more. I mean, there's all kinds of, but this is in terms of fuels that you could actually go into the boiler with. Now, I hunted up, because I know you guys get tired of hearing me just drone on all the time. So I hunted up a couple of YouTube videos here. So let me see, one of them, solar power. So this is solar thermal. So this is one of the topics on your presentation. Guys out there, I'll send out the link to this. I mean, it's only got about 3 minutes left, so I apologize if you can't hear it. I don't know. But anyway, I'll send out the link so you can watch it later. Sir.
So what they did is they put a little, I guess, heat magnet sort of thing on the top, and then they used the mirrors to point the sunlight at that. And then they have the salt.
It's a molten salt. And they like that because it has an extremely high heat capacity. And so what happens is even, they get that stuff heated up, they get so much energy stored in it. Even after the sun goes down, they can still run the plant, depends on load, for probably, 3-4 hours into the evening. And that's when there's still a lot of peak load out there. And so they can continue to operate even after they've lost their input energy, because there's so much energy stored in that salt. But, I mean, it's basically a boiler. It's kind of a funny looking boiler, and we're not burning anything. There's no combustion, but those heliostats, man, they're engineered to track the sun. As the sun moves across the sky, they reposition themselves to focus, maximum light up there on that tower to keep putting that energy into that salt so they can keep making steam. I mean, and but it's just a Rankine cycle. Now, how many feed water heater, I mean, you'd have to get into the design of a particular plant. I've never seen a detailed design on solar thermal because there really aren't very many of them out there. I don't think they've ever really taken off. This one was obviously built. There may be a few in California, but I don't think that technology is going anyplace right now very quickly. But of course, it just tell you if the federal government decides, hey, we want to support this, and all of a sudden we start paying 20% of the price, all of a sudden economically it becomes very feasible, and all these private companies will jump on board, if the feds will pay enough of it. I mean, like I said, it's hard to know where the industry is going to go long term. There may be some new discovery or something in 5 years, 10 years. I mean, look at life before the internet and all that stuff. And then all of a sudden they came up with the internet. I mean, my God, that has just revolutionized the whole world. And so who knows what's coming next? It doesn't happen very often, but it does happen. And there could be something out there in the energy field.
Do they have to put these in just super open areas? I assume the desert's a pretty solid choice on where to put it. But like they want a place with low cloud coverage.
Well, okay, so yeah, I mean, they want someplace that has, a lot of solar insulation, and, if you don't have much cloud cover, all the better, because, cloud cover, rain, all that's going to knock down what you can generate. And that's one of the issues is the places, like I guess in Death Valley, California would be a great place. But then you've got to build transmission lines. And Death Valley, I'm sure, is a protected wildlife natural area. And so you're going to build all these big transmission towers right then, I mean, it's like, what if you want to cross the Grand Canyon? Are you going to somehow build transmission lines across the Grand Canyon? Probably not. Even if you could, technically, they're not going to let you. And so, let's say you got to pull this power 1,000 miles. Well, everybody that owns land in between says, NIMBY, not in my backyard. I don't want that stuff coming across my land. It's gonna destroy my property values, because then, we had this deal on Buck Mountain outside Cookeville. There's a bunch of people lived up there, and TVA needed to pull another main supply line into Allgood because, the existing line was saturated, and Allgood's growing this was probably 10 years ago. And all those people where they were going to build that transmission line banded together, about 50 of them, put some money in and hired attorneys and filed suit against TVA to stop the transmission line from coming across their property. Well, at the end of the day, they lost, but they probably slowed it up a year and a half or 2 years by being in court. And, TVA had to show need. And, once you file suit against them, then TVA has to go through all this legal processes. Legal system operates very slowly. And so they held them up for, I don't know, a year and a half, 2 years. But at the end of the day, the line got built, and it's there today. Sir?
One other quick question. So the panels that people put on don't like go into like a Rankine cycle. So
Oh, no.
like what's the difference there?
Well, okay. So that's photovoltaic. And I think you might want to check your email. I think earlier in the course I sent out a couple of links. One of them was pretty long. Yeah, one of them was long. It was about solar PV in the utility industry, but the other one was about 2 minutes or 4 minutes. And it described, because I'm not an electrical engineer, and it described roughly how these PV panels work. They're semiconductor materials, and they're doped. They dope one of them with electrons, and they dope the other one with holes. Yeah.
Some of this actually B, and the B element has holes in it, the phosphor has an extra electron. It makes this zone in the center that causes a charge difference.
Yeah, some kind of electrical magic, you know, with semiconductors. But I mean, if you can't find that, you could just get on YouTube and type how does a solar PV panel work, and you can find 15 or 20 videos and just watch a couple of them, and it'll show you. I mean, that's beyond the scope of what I'm going to do in here. But you know, that's one of the topics for your project, and so you'll have to look into that to the point that you can at least make a couple slides, or you can steal some images off a presentation like that. But you know, that's one of the reasons I want to do that renewable project with you, or have you do it, is because it'll get you into each one of those topics. And you know, I don't expect you to be an expert, but you can look into each one of those and get some kind of an idea how they operate. Speaking of that, let me see. Where is this? It may be. Here we go. And I'm going to send this out. This is a document. This is a study by, I don't know, one of the national labs. And I was just Googling around. I was thinking about solar, and I don't know all that much about solar. This is solar PV. And I'm sitting there going, well, you know, I was thinking about Kingston. So Kingston's design capacity was 1,900 megawatts, roughly 2,000, not quite, but pretty close to 2,000 megawatts. Well, if we wanted to build a 2,000 megawatt solar PV plant around here, how much land would it take? And so I dug this, I found a rule of thumb number, and then I thought, well, maybe I can find something better. And I came up with this, and this is a big study. But anyway, and so this is just executive summary 1. I've not read this whole thing, but take a look at it. So for large PV, which would be like utility scale, direct area, total area, they say this is acres per megawatt AC. So it's 7.9. That's kind of interesting. So I said, well, okay. So 7.9, and I'm going to do 2,000 megawatts. Well, that's 15,800 acres. That's a chunk of land. And then I'm sitting there in store one. I said, well, I don't really do much math with acres. It's not one of my common units. So I looked up the conversion to square miles. So if you multiply acres by 0.0015625, you get square miles. Now, square miles, I got a pretty good idea what that is. So times recall 1. So that's 24 rounded up 0.7 square miles. Well, a pretty good sized chunk of land now. And so if you take the square root of that, you can see what, you know, if it was square, what the side would be. So square root, 4.96. So basically 5 miles. So for a 2,000 megawatt solar PV, you're going to have 5 miles square of land. That's going to be, where are you going to find 5 square miles that you can go out and buy? I mean, I don't know. You're going to declare eminent domain and expropriate a bunch of farmlands out there? You know, I don't know. Now, federal lands, you know, maybe the federal government would want to, you know, sell you at a reasonable price, or a TVA at a reasonable price, you know, a big chunk of land. And then, you know, you start thinking about it. So if you want, so that would be probably peak, but that's not storage or anything. So what if you want to be able to provide that 24 hours a day? Well, you're going to have to put in twice that much, right? Or probably more than twice that much. And then you're going to have to put a whole bunch of batteries to store the power, because last time I checked, it's still getting dark at night. And so those PV photovoltaic cells are not going to produce anything at night. So all of a sudden, let's see, square that. So that basically 25 square miles times 2, I'm going to say 2.2, probably turns into 55 to 60 square miles. For 2,000 reliable, well, and that's peak. The question is, I'm not sure how, well, it wouldn't necessarily be reliable, because if you get a big cloud cover come through, then you're not going to be able to reach your peak capacity. So it's not even really firm. So that's the square root of that say 50, it's 54.3 on the calculator, square root is about 7.4 miles. You see where the difficulty is? It's not that you can't do a little bit here, a little bit there, and it worked really well. But when you start trying to replace these central station generators, like this nuclear plant, like Watts Bar, how many megawatts is Watts Bar?
Probably somewhere between 21 to 25 megawatts.
2,100?
Yeah, because each, maybe closer to 25, honestly, because each unit would be around
Okay.
12 to 1,300.
So Watts Bar would be a little bit more, is a little bit more than my 2,000 here. And how many square miles is Watts Bar on? Like 1, maybe 2? Yeah, maybe 1. So, I mean, I'm not anti-renewables, but I'm just saying you have to be realistic about it and see what you can get and what you can do that doesn't fly in the face of common sense. Okay. Enough of that. Let's go back to my beautiful yellowed notes here. So those are common fuels used, maybe some other stuff. Other possibilities, like pulp and paper mills. Of course, that's pretty small scale. That's not utility scale, but we can potentially do some chemical recovery. Volume reduction from municipal solid waste can actually be combusted. It's not easy to combust. It doesn't combust very efficiently, but I guess it's renewable because we keep generating municipal solid waste every day. And we've already talked about the size, design considerations. Look at all the stuff. I mean, I think you'd probably come up with this on your own, but we have to produce a steam generating system which meets the capacity requirements in the most economical package. Now, economical these days is probably heavily driven by environmental, because everything is very environmentally driven. But we got to worry about fuel characteristics, depending on emissions, what's going to come out, what is it going to take to clean it up, make it acceptable, what kind of efficiencies can we get out of it? What about maintenance operating costs? I mean, I wonder about those molten salts. I would think that would be pretty corrosive stuff. And so is all that piping going to be stainless steel to stand up to that? Man, stainless steel, expensive, So if everything that touches that molten salts got to be stainless steel, that's really going to up the price on the plant. Maintenance operating costs, regulatory requirements. That's why nuclear gets just pounded on regulatory requirements, and even the coal plants. I mean, at Kingston, for years they've had these requirements. They call them continuous emission monitoring. It's called SIMS, continuous emission monitoring systems, I guess. And so these big plants, they have to have continual monitoring of their stack and what goes up. And I mean, if that equipment goes down for any length of time at all, they're looking at a huge fine. I mean, it's got to be calibrated, on a regular basis, probably annually. And all those environmental regulations actually created a new industry in SIMS, in manufacturing the equipment, selling the equipment, installing the equipment, maintaining the equipment. TVA had to establish a whole new department when all that stuff came along. Because back, 30 years ago, that wasn't a requirement, but it is now. They have to monitor all that stuff, and they have to stay within their permitted limits. Some new technologies. I'm not going to get into that stuff right now. I have pressurized, fluidized bed combustion systems. That's not really new technology anymore. Those boilers are out there, but all that stuff's going to go away because they burn coal. And then combined cycle, we've talked about that some. Cogen, big deal, but I think you guys are probably a little bit up to speed on cogen. You know, we talked about that. Look, some key power plant subsystems. Transportation, how are you going to get the fuel there? Oh, I know, I do. Oh, that's right. I've got another, talking about biomass a little bit. I've got another, yeah, 2 minutes. Well, I got to take it back. There it is. Oh, let's get it planned. All right, that was kind of short and sweet, but you know what? Other than putting biomass in the boiler, it sure did look a lot like a Rankine cycle, didn't it? So, all right, that wasn't very exciting. Okay, so back to the subsystems, you know, transportation, you know, think about it. I mean, if you're burning all that biomass, how are you going to get it there? You're going to put it on the back of a diesel truck and drive it in? How's that help your emissions? You know, you may be burning renewable biomass, but that oil you're burning to transport it there, that's probably not so renewable, you know? So all this stuff, it's complicated. Our railroad access, that's probably better, probably more efficient than trucks, but still, what do you think that, what kind of fuel do you think that railroad engine's burning? Probably not renewable, you know? So, I don't know. I won't go into my Keystone Pipeline discussion again. But, you know, in the overall evaluation of a fuel, you got to figure out how you're going to get it there. Like at TVA at Kingston, they bring it in by rail car, which isn't too bad. There are plants that bring it in on barges. They can float it down the river. That's a whole lot better. And like Plant Miller, Southern Company down in Alabama, they have to truck it in. I drove in we had a meeting down there one time, and we were on that road going in, and I mean, there was a steady stream of semi-trucks coming in, loaded, coming out, empty. I mean, it was just, they were just all over the place. And you're sitting there going, man, couldn't they get this thing, build a railroad spur over here, make this better? But there are plants out there, coal plants and others, that have to, truck in the fuel. And the scale of the generation and the size of the equipment, I mean, it's hard to imagine until you see it, how large this stuff is. So, fuel handling is huge. How are you going to store it? At Kingston, they got the big coal pile, and you can tell kind of what season you're in by how tall the coal pile is. So it's like they bring it in September and October, and they pile up the pile, and then they use it down in the winter. And so coming into the spring, it's pretty low, and they pile it back up again. So you can, if you know the temperature outside and the size of the coal pile, you can estimate what season of the year you're in. What do you have to do fuel prep? Man, what a big advantage of natural gas coming in. What do you got to do? Locate your plant close to a pipeline. Install a big pipe, some pressure reducing valves, and open the valve. That's pretty easy compared to, rail cars. At Kingston, in the wintertime, the coal will freeze into the cars. And so they have specially built cars that the bottom will fall out of, and the coal will fall down in a pit, and then they got conveyors to move it. But guess what? When it freezes in the car, they open the door and nothing comes out because it's all frozen. Well, that's not so good. So if it's frozen, what they have is they have this huge heating shed. It's like either 2 or 4 megawatts of heating elements. And it's just an open shed. It's open. The doors there aren't doors. Well, there are doors, but they stay open on the ends because the rail cars are going through, and they slowly pull that rail car through there, and it's probably as long as 4 rail cars, and they pull it through, and they just blast the side of that rail car, top, bottom, all over, with heat from electric resistance heating elements, and enough to melt enough of the water so when they open the door, the coal will fall out. When I first started going to Kingston, they used to decouple the car, and they had this crane-like lift that would grab the car and turn it upside down and like shake it to get the frozen coal out. Well, they decided that was just too hard because I guess they dropped a few cars here and there. And so they came up with the idea of the heating shed, which is what they still use today in cold weather. So we got fuel handling. If you're coal or if you're doing the wood, you're probably going to have to chop it up, hog it. At the coal plant, we pulverize it into like face powder, and then somehow we've got to get it into the boiler. So you got transport, whatever fuel that you've got. Air. So, where's the air going to come from to support combustion? That's going to come from outside. You can't afford to provide pure oxygen. It's expensive. The oxygen in the air is free. And so we're going to pull air in. And so the way large boilers, furnaces are built, they have what's called a forced draft fan that blows air into the boiler. On the backside, on the emission side, we've got an induced draft fan that sucks air out. And by controlling the capacity of those fans, we can set the furnace pressurization. Okay, so that would be for like probably a balanced draft. If you want it to be positive, well, you blow in more than you suck out. If you want it to be negative, you suck out more than you blow in. So generally speaking, they want to keep a slight negative pressure in the boiler because they do have doors on the side. And if you open one of those doors someplace around the fireball, you just as soon not have 2,500 degree gases blow out in your face. So if you're slightly negative in pressure, if you open the door, then some outside air gets sucked in, but at least you're not blowing hot, combustion gases out on people that might occasionally open a door. So generally speaking, they're slightly negative. But it's the balance between those fans that sets the pressurization. Okay, I think that's pretty good. We're just about at the end of class time today. So we'll go ahead and cut this off, and we'll continue through some of these notes. Certainly be working on your thermo stuff, and you can start thinking about your project for sure. And we'll be back in touch on Tuesday. So I hope everybody has a great weekend, and see you on Tuesday.